Okay, so if you've ever gone deep into physics, you've definitely come across the name Irodov, right? And that name, it brings up some feelings. A little bit of fear, a whole lot of respect. His problems are just legendary for being, well, for being absolute brain breakers. They push you right to the edge. And today, we're going to take on one of those legendary challenges, problem 1.14, and we're going to tear it apart piece by piece.
You know, the funny thing is, Irodov basically warns you right from the start. In the preface, he says his book is for students in an, quote, advanced course in physics. And let's be real, that's code. That's code for, hey, this isn't your high school plug-and-chug physics. Nope, this is about really getting the core concepts. And that's exactly what we're here to do.
So, here's how we're going to tackle this. First up, we'll lay out the challenge, the problem itself. Then we're going to decode it, pull out all the important bits. We'll solve it from 3 different perspectives, from the ground, from the train, and from this really cool same spot frame. And at the end, we'll get into why this idea of reference frames is just so fundamental.
All right, section 1, let's get right into it and look at the problem statement.
Okay, so here's the setup. You've got a train, it's 350 meters long, and it starts from rest with a constant acceleration. Pretty standard so far. Now, 30 seconds into its journey, bam, the headlight at the very front flashes. We'll call that event 1. Then, a full 60 seconds later, the tail light at the very back flashes on. That's our event 2. See? The setup itself sounds pretty straightforward, right? But trust me, the questions this problem asks, that's where the real magic happens. Okay, part 2, decoding the problem. You know the drill. Before you can solve anything, you got to get your facts straight. Let's lay out all our knowns and unknowns.
So here's our toolkit. We've got L, the length of the train, 350 meters. We've got W, that's the constant acceleration. Then there's T, the time until that first flash goes off, which is 30 seconds. And finally, tau, the time between the 2 flashes, which is 60 seconds. Got it? These are the puzzle pieces we're going to use to solve this thing.
So what are we actually trying to find? This is the key. Irodov is sneaky. He doesn't just ask for the distance. No way. He wants to know what's the distance between the flashes if you're standing on the ground. And then, what's the distance if you're on the train? And just for fun, he throws in this amazing curveball, find the velocity of some special frame of reference, let's call it K, where both flashes happen in the exact same spot. How cool is that?
Okay, on to part 3, the view from the ground. Let's put ourselves on the platform, totally still, just watching this train go by. From our perspective, how far apart are those 2 light flashes?
So, to get this done, we need to pinpoint the location of each event. Event 1, the headlight flash, happens at time t. Easy enough. Its position, x1, is just your classic 1/2 at squared. Now, event 2 is a bit trickier. It's the tail light, and it happens at a later time, t plus tau. So what we do is find the position of the front of the train at that later time, and then we just subtract the whole length of the train, L, to find where the back is. Then, the distance we're looking for, delta x, is just the absolute difference between x2 and x1. Simple as that. And when you do a little bit of algebra, you subtract that first equation from the second, it all collapses down into this really nice, clean formula. You see that the distance, delta x, depends on the train's length, the acceleration, and those 2 time values. All that's left to do now is plug and chug with the numbers we already have.
And when you run the numbers, you get 240 meters. So there's our first answer. If you're standing on the ground, those 2 flashes are 240 meters apart. Okay, lock that number in your brain. Now, let's hop on the train.
All right, part 4, the view from the train. So now, we're changing our frame of reference completely. We're on board, moving right along with it. From here, how far apart are the flashes?
Now, this is maybe the easiest part of the whole problem, but it's also one of the most important ideas. Think about it. If you're sitting on that train, are the headlight and the tail light moving? Relative to you? No, they're fixed. They're part of the train you're on. So the distance between them is, well, it's just the length of the train, right? It's always the length of the train. It doesn't matter when the lights flash. From your seat, the distance is constant.
And look at that. This is the whole point. We have 2 totally different observers getting 2 totally different answers. From the ground, it's 240 meters. Why? Because the train was moving in between the 2 flashes. But if you're on the train, it's 350 meters, the full length. This is huge. It tells us that distance isn't some fixed, absolute thing. It literally depends on how you're moving.
Okay, now we get to my favorite part, the real brain twister. We need to find this hypothetical same spot frame, this frame K. Imagine you're in a car driving alongside the train.
What speed do you need to be going so that from your perspective, both the headlight flash and the taillight flash happen in the exact same location?
So how on earth do we figure that out? It's actually way more straightforward than it sounds. For the two flashes to happen at the same spot from your point of view, you have to be at the location of the first flash when it happens, and then you have to travel and arrive at the location of the second flash at the exact instant it happens. What does that mean for your velocity? Well, it has to be the distance you traveled divided by the time it took. And what's that distance in time? It's the distance between the events as measured from the ground divided by the time between the events, tau.
And hey, we already have those numbers. We found the distance in the Earth frame was 240 meters. We were given that the time between them was 60 seconds, so you just do the division. 240 divided by 60, and you get 4.0 meters per second. That's it. That's the speed of frame K. If you travel at a constant 4 meters per second in the same direction as the train, you will see both lights flash at the exact same point in space.
So there we have it. We've solved it. But let's step back for a second. What's the big picture here? What's the deeper lesson that a problem like this is trying to teach us about physics?
Let's just put all our answers side by side. For the person on the ground, the distance was 240 meters. For the person on the train, 350 meters. And for our special observer in frame K, moving at 4 meters per second, the distance was 0. Think about that. We have the same two events, a light flashes here, a light flashes there, but how far apart they are depends entirely on who's doing the measuring.
And that is the big revelation. This problem, it's more than just a clever kinematics puzzle. It's a perfect gateway into one of the most mind-blowing ideas in physics, something Einstein would later take to a whole new level with relativity. It shows us that there's no absolute universal ruler for space. The distance we measure, and even the time we measure, it's all relative. It's tied to our own motion.
So I'll leave you with this final thought to chew on. If just moving differently can literally change where events happen in your world, what does that really say about the nature of space and time? It kind of suggests they aren't this fixed, empty stage where things happen. It suggests they're part of the action themselves, a dynamic, connected fabric. And that, right there, is the incredible power of one really good physics problem.